Alright, let's have a look at carboxylic acids. They're a really important functional group and they're present in all sorts of chemicals you come into contact with every day. So the carboxylic acid group is defined by the carboxyl functional group. There it is there. It's really nice to be able to draw out the structure of the carboxylic acid in multiple ways. This is the most sort of precise organic chemist way of drawing it. We're showing all of the bonding and lone pairs of electrons on the oxygens. But these are a couple of shortcut ways that we draw when we're short on time or just want to abbreviate things. They can quite often lead to a little bit of misunderstanding because, it doesn't deliberately show you that there's a CO double bond and then a CO single bond and so on. So the general formula of an aliphatic, that means hydrocarbon R group, carboxylic acid is RCOOH, and aromatic carboxylic acids are quite common. So these are things like benzoic acid, which we abbreviate the R group as AR to show us that it's an aromatic. Now, there's a number of really important derivatives we can make from carboxylic acids, and the general formulas are shown here. So there's acid chlorides or acyl chlorides. There's acid anhydrides, esters, and amides, and each of these are important in various ways. Now, acid halides or acid chlorides, as the most common of that group, are highly reactive. So they have a carbonyl group, CO double bond, and then a halogen attached to the carbon that has the carbonyl oxygen attached to it. So that halogen is electron withdrawing and CO double bond is electron withdrawing. So that carbon of the carbonyl group is very partial. It has a very substantial partial positive charge. One of the simplest, or probably the simplest acid chloride is acetyl chloride, which, and like many acid chlorides, if you are exposed to this, it will make your eyes water because it's so reactive towards water that when it gets into your onto your skin, then it will hydrolyze to hydrochloric acid plus acetic acid, and the HCl will burn your skin, and if it gets in your eyes, then it'll burn your eyes. So the abbreviation for acid chlorides is RCOX, and just Cl if it's a chloro group. Acid anhydrides are not quite as reactive as acid chlorides, but still quite reactive. They're a functional group where we have two acyl groups. So acyl groups are where we have the CO double bond and then an R group. So that's an acyl group there and there. So, and then we connect those two acyl groups through a central oxygen atom. So this is the simplest common acid anhydride, which is acetic anhydride, or the IUPAC name would be ethanoic anhydride. They can be symmetrical or mixed, so it doesn't have to be the case that this group is the same as this group, but by far the more common acid anhydrides do have the same substituent on both sides. Esters, I'm sure you've heard of esters before. They're really common functional groups. They're present in many interesting molecules. So esters, we have the acyl group connected to an oxygen atom that then is connected to an alkyl group. So we have one alkyl group directly attached to the carbonyl carbon and one alkyl group attached to the oxygen that is then connected to the carbonyl carbon. So these groups are quite different. One is bonded directly to a carbon and one is bonded directly to an oxygen. And this one is ethyl acetate, which is a really common solvent in organic labs. Amides is the final of those four functional groups that we wanted to look at. Amides of carboxylic acids are also really important. They're a structural subunit of peptides and proteins and lots of interesting molecules. The simplest amide that you would commonly come across is acetamide, which is we have an acetyl group attached to an NH2. So amides have the acyl group, which is the R group attached to the CO double bond, and then a nitrogen atom. If we put alkyl groups onto the nitrogen, then if we put one alkyl group on, we call that a secondary amide. If we put two alkyl groups on, we call that a tertiary amide. And if we have no alkyl groups, then that's a primary amide. So each one of these is an abbreviation for a particular term. So that's primary, there. This is secondary, and this is tertiary. Okay, so how do we name carboxylic acids? Well, the carboxylic acid is always going to be the end of a chain. So these are relatively easy to name. We just start at the carboxylic acid. We can number the chain towards the substituents, looking for the longest chain, longest contiguous set of carbon atoms, and we're going to end the name with oic acid. So we drop off the E and get oic acid at the end. And so this compound here is 3-methylbutanoic acid. But many compounds that have been known for a long time have common names. This is also commonly known as isovaleric acid. This one here is trans-3-phenylpropenoic acid. What are the properties of these molecules? Well, in the liquid and the solid state, carboxylic acids can form hydrogen bonds to each other. And they're really strong hydrogen bonds because we can get dimers formed where we get hydrogen bonding between the carbonyl group of one carboxylic acid and the OH of the other carboxylic acid at the same time as the carbonyl group of this compound hydrogen bonds to the OH group of this carboxylic acid. So it's a symmetrical dimer, and each one is adding to the overall strength of that hydrogen bond. So those dimers are extremely strong. Because of that, and because they can also intermolecularly hydrogen bond, the carboxylic acids have a very high boiling point for the size of the molecules. They're very polar, and they form strong intermolecular hydrogen bonds, and that keeps them in solution, and it makes it have a very low vapor pressure. Long hydrocarbon chains with a carboxylic acid at the end, we call those fatty acids. And they're common in biology, and they form waxy oils and solids. Okay, so here's a short chain fatty acid. We've got a waxy hydrophobic tail, which is a hydrocarbon tail, and a carboxylic acid end, which is hydrophilic, or it loves water because it's polar. And so this compound has a solubility, it's fairly low, 0.2 grams per 100 mils in water, but it will help other compounds dissolve, a bit like a soap. So these compounds can act a bit like soaps because they have a polar head group and a lipophilic tail. They're more soluble in water than alcohols, ethers, aldehydes, and ketones of similar molecular weight because of that polar head group. Looking at the physical properties of carboxylic acids, because of that polar hydrogen bonding group at the end there, acetic acid relative to propan-1-ol, which has a similar molecular mass, and propanol, which has a similar molecular mass, acetic acid has a much higher boiling point, certainly a lot higher than the aldehyde and a bit higher than the alcohol. It also is very soluble in water. If we go up to the 4-carbon carboxylic acid, butanoic acid, it has a molecular weight of 88, and compare that to the alcohol of a similar molecular weight, it's higher boiling once again, and it has very high water solubility, essentially infinite, so it's infinitely miscible. Even with a 6-carbon carboxylic acid, we have quite high solubility. 1 gram per 100 mils in water is quite soluble for an organic compound, whereas the alcohol with similar molecular weight is only 0.2 grams per 100 mils, and the aldehyde is only 0.1 grams per 100 mils. And once again, the boiling points have that same trend. Now, once you get up to an 8-carbon chain, so octanoic acid, then we finally have a long enough lipophilic tail that it's not really very soluble in aqueous solvents, but is a little bit soluble, whereas the alcohol is really not soluble at all. And in fact, octanol is used with water as a way of finding out the way the molecules would partition between aqueous environments and cell membranes. So that's a really important property, the partition between octanol and water. Now we can classify the reactions of carboxylic acids in 2 major types. There's acid-base reactions, and then there's nucleophilic acyl substitution, or nucleophilic acid substitution. And that's because the carbonyl group is electrophilic. Electrophilic meaning that it's electron-loving, so it's seeking out a source of negative charge or electron pairs. So when this bond here breaks, we have acid-base chemistry. When we do stuff here, we're talking about nucleophilic acyl substitution because they're substituting what is attached to this acyl group. We basically never see chemistry where this bond is going to break. Not in undergraduate chemistry anyway. So looking at the acidity of carboxylic acids, they're weak acids. They're not strong acids like hydrochloric or nitric acid. The ionization constants or pKa values are fairly small, or the pKa values are fairly high relative to strong acids. So Ka values in the range of 10 to the minus 4, 10 to the minus 5 mean pKa's is the range 4 to 5. So for acetic acid, we're looking at the equilibrium between acetic acid and water, going to acetate plus the hydronium ion, and that equilibrium lies well over towards the left-hand side, equilibrium constant of 1.8 by 10 to the minus 5, which corresponds to a pKa of 4.74. And so acetic acid is a fairly weak acid. But they're stronger acids than alcohols because we have what's called resonance stabilization. We can draw more than one Lewis structure for a carboxylic acid, and that helps to stabilize the negative charge. Particularly, the more than one Lewis structure that we can draw is to do with the carboxylate that we form when we lose that proton. There's no comparable resonance stabilization of similar alcohols when you form the alkoxide. So when we take a proton off acetic acid, we generate the acetate anion, and we can draw two different resonance forms of that anion. So for resonance structures, we use this type of arrow, double-headed arrow. And we can draw curly arrows to show how electrons move to go from one resonance form to the other. So that resonance stabilization does two things. It gives two forms to the molecule, and resonance is a general stabilizing feature, but it also smears the negative charge out over two oxygen atoms. So we know that nature abhors having a negative or a positive or any charge in a small confined space. So spreading out the negative charge over two oxygens helps to stabilize that negative charge and make that a more stable anion, and therefore make the conjugate acid a stronger acid than it would otherwise be. So if you look in with computational chemistry at the structure of the carboxylate anion, we actually see that it does not have the negative charge of one or other of the oxygens. It has it equally distributed amongst the two oxygens of the carboxylate. So these two oxygens are equivalent to each other. And so they each have sort of half of a negative charge. Okay, so what happens if we put electron-withdrawing substituents nearby to the carboxylic acid or the carboxyl group? What happens is we increase the acidity of the carboxylic acid because we increase the stability of the carboxylate anion, the conjugate base. Okay, so acetic acid, if we look at acetic acid, pKa 4.74. Remember, if we go to lower pKa's, we're talking about stronger acids. So when we put a chlorine atom onto acetic acid, we get chloroacetic acid, and we go almost 2 log units lower in pKa. That means almost 100 times stronger acid when we go to chloroacetic acid. If we put a second chlorine on, dichloroacetic acid, we drop by about 1.5 pKa units. So that's about between 10 and 100 times more acidic. And then finally, trichloroacetic acid has a pKa of 0.7. So this is really up there with strong acids like HCl and nitric acid. It's a very strong acid, and certainly if you spill trichloroacetic acid on your skin, it'll give you a very nasty burn. So that's looking at how many halogens we put onto the molecule. What about where we put them onto the molecule? In acetic acid, there's only one possibility. We can put it onto the methyl group. But what about butanoic acid? If we put the chlorine adjacent to the carboxylic acid, it lowers the pKa. If we put it one further removed to the 3 position, the pKa is not as low. If we put it one further again, so make 4-chlorobutanoic acid, then it's a little bit less strong in effect again. And then finally, butanoic acid, where there's no chlorines, is 4.82 pKa. So as we move the chlorine closer, we're getting to stronger and stronger acids. So why is this the case? Well, it's all about stabilizing that conjugate base. So when we lose a proton of butanoic acid, we've got water here, and we're going to lose a proton to generate H3O plus and the carboxylate. And we know that we can draw resonance forms for this, where we put the negative charge onto the other oxygen atom. Now, if I put an electron withdrawing group onto this position here, that electron withdrawing group is going to pull electron density away from that carbon. So it's going to be delta negative, this is going to be delta positive, and it helps to stabilize the negative charge. Okay, and that's called induction, or an inductive effect. So, and that will happen on both the carboxylic acid. There'll be an inductive effect on the carboxylic acid and on the carboxylate, but the effect is really important on the carboxylate because it's got a negative charge to stabilize, and so this helps to favor the right-hand side of the equation more than it helps to favor the left-hand side, and so we get the right-hand side being favored more and a lower pK and more of that carboxylate being formed. Okay, so when we take a carboxylic acid and we treat it with a base, we'll get acid-base chemistry. So a strong base like sodium hydroxide will fully deprotonate the weak acid, such as benzoic acid. So benzoic acid is only slightly soluble in water, but when we treat it with sodium hydroxide, we generate sodium benzoate, which has a solubility of 60 grams per 100 mils in water. So it's really water soluble. So we can actually use this to separate out carboxylic acids from other compounds that are not acidic. We can treat them with a base, and then the organic compound, the carboxylic acid, will go into the aqueous phase, and we can separate it that way. We also make water-soluble salts with other bases, such as amines and ammonia. One reaction that can occur between carboxylic acids and a base is with sodium bicarbonate or sodium carbonate. So sodium bicarbonate is not a strong base, but when it reacts with carboxylic acids, it generates both the sodium salt of the carboxylic acids, so the sodium carboxylate, and also carbonic acid. So carbonic acid is HOCOH, like that, and that loses carbon dioxide. So when it loses carbon dioxide, that's a gas, and that disappears from the system. And so even though it may be a weak base, the whole equilibrium is drawn over towards the right-hand side because of the loss of the carbon dioxide. So overall, this is the balanced equation. We've got acetic acid plus sodium bicarbonate in water, giving sodium acetate plus carbonic acid. Carbonic acid then spontaneously loses CO2 and water, and overall we're getting acetic acid plus sodium bicarbonate, giving sodium acetate plus carbon dioxide plus water. And the carbon dioxide will just bubble off the mixture. And I'm sure that many of you will have done this in the kitchen at home as a little home experiment where you mix vinegar and sodium bicarbonate, which is also known as bicarb of soda or cooking soda and things like that, and you'll see bubbles form from this reaction. Okay, so you can use this chemistry, like I said before, to separate compounds on the basis of the carboxylic acid being acidic. So if we had a mixture of, example, benzyl alcohol and benzoic acid, both of these are not very soluble in water, so we dissolve them in an organic solvent, but then we treat that organic solvent with a strong base. Now the strong base will deprotonate the benzoic acid to turn it into sodium benzoate. That now is water soluble and goes into the aqueous phase. So that's why this is colored blue. It's in the aqueous phase. Whereas the alcohol is not affected by the sodium hydroxide. It's not acidic. So it stays in the ether layer. We can distill off the ether. We can separate the ether from the water. We can distill off the ether and get the benzyl alcohol. Similarly, we can acidify the aqueous layer over here. That will make the sodium benzoate back into benzoic acid. That's no longer soluble in water, and so it crashes out as a solid, and we can filter it off and isolate it. So we can separate these two things based on these physical properties. Okay, so the other major type of reaction of carboxylic acids and their derivatives is nucleophilic acyl substitution. So now we're talking about exchanging what is attached to the carbonyl group with something else. And as the name implies, it's reaction with a nucleophile. So the key step is addition of a nucleophile to the carbonyl carbon, and then formation of a tetrahedral carbonyl addition intermediate. So when we get the nucleophile add, we can draw a curly arrow that makes it attack this position here. Electrons go out onto that oxygen, and we get an intermediate. So we don't really see this intermediate. Sometimes it can be isolated, or we can do things to it, like trap it out with other species. But generally, it doesn't last long, and it collapses by the CO double bond reforming, and then losing the Y group here as a leaving group. So it takes a pair of electrons away and is a leaving group. And so we've exchanged out what was attached to that acyl group. Okay, so when we do these nucleophilic acyl substitutions, there's an order in which molecules will react, and it's related to how stable is the anion of the group that is leaving. So if we go back to the previous slide, the leaving group here has to depart in this step. And so if that's stable, that would be easy to do, and if it's unstable, it would be difficult to do. So we know that amide anions, so this is very confusing, I know, but amide anion is different to amide, the functional group, or amide, the neutral species. So amide anions are nitrogen with a negative charge and two R groups. That's very unstable, so it doesn't like to act as a leaving group. Similarly, alkoxides are a little bit better, but they're still fairly unstable. Carboxylates are better than alkoxides because we've got that resonance stabilization. And halides are quite stable, so particularly iodide, bromide, chloride, they can act as leaving groups very readily. And this is, you might notice, the opposite in the terms of their basicity. So halides are not very strong bases because they're very stable, and so they help to make their conjugate acids very strong acids. Whereas amide anions are strong bases, and their conjugate acids are weak acids. Okay, so the reactions of carboxylic acid derivatives and carboxylic acids are shown here. So carboxylic acid derivatives will react with water to give carboxylic acids. They'll react with ammonia to give amides. They'll be reduced with some reagents to give aldehydes, and then sometimes react further to give primary alcohols. They'll react with species called Grignard reagents to give ketones, and then they can react further to give tertiary alcohols, and they can react with alcohols to give esters. And that's a very common experiment, to take an acid, carboxylic acid or carboxylic acid derivative, react it with an alcohol, and end up with an ester. So reactions with alcohols, like I said, are one of the more important examples. The Fischer esterification is probably the most famous and most important of these. So you treat the carboxylic acid with an alcohol. It really won't do anything unless you heat it to extreme temperatures, unless you add an acid catalyst. And then it will give the ester in good yields at relatively accessible temperatures. So in practice, we would take a carboxylic acid like acetic acid, treat with ethanol, and a strong acid like sulfuric acid, and we'll generate the ester, in this case ethyl acetate, and the byproduct will be water. Now this is an equilibrium, so we're going to have to do something to shift the equilibrium in one direction or another. Either use an excess of one of the reagents, or remove one of the products or starting materials to drive the equilibrium in one direction or the other. Acid anhydrides are much more reactive than carboxylic acids themselves. So acid anhydrides will actually react with alcohols to give 1 mole of an ester and 1 mole of a carboxylic acid as the byproduct. So we can take reagents like acetic anhydride, and react it with ethanol, and we'll get ethyl acetate plus acetic acid. And now this is not reversible because the product ester is so much more stable than the starting material acetic anhydride. Similarly, we can take salicylic acid and treat it with acetic anhydride, and we'll get acetyl salicylic acid, otherwise known as aspirin, which is a really common undergraduate experiment. And the byproduct is acetic acid. Okay, amides are really stable functional groups, so they don't react with alcohol under normal experimental conditions. So the reactions of carboxylic acids are with alcohols and acid, they'll give esters. Acyl chlorides with alcohols will give the esters directly without any need for a catalyst. Same with acid anhydrides, they'll give esters and a byproduct of a carboxylic acid. Esters with other alcohols can undergo an exchange in the presence of an acid catalyst to give a different ester and exchange the alcohol. So we've exchanged one alcohol for the other. So the ester has changed its group here. That'll be an equilibrium. So once again, we might have to choose the conditions to force the equilibrium over to the way that we want it to go. Amides are very stable. They really don't react with alcohols at all. If we look at acid, chlorides, anhydrides, esters, and amides with water, we have similar reactivity. So acid chlorides hydrolyze with water very readily to give carboxylic acids, as do acid anhydrides. Whereas esters with water, we need more forcing conditions. So we need either a strong base, and then we'll hydrolyze the ester to give the carboxylic acid, and then the carboxylic acid will be deprotonated by the strongly basic conditions to give the carboxylate. So the sodium carboxylate and a side product of an alcohol. We can also do that hydrolysis of the ester. We call that a saponification. We can do that under acidic conditions, and that'll give the carboxylic acid plus the alcohol. Similarly, with an amide, we can do base or acidic hydrolysis, but amides, because they're so stable, these quite often need to be very forcing conditions, high temperatures, strong reagents, and long reaction times to get the carboxylate in the terms of base conditions, or the carboxylic acid plus an amine or ammonia as the other side product. Okay, so hopefully that's given you a little bit of an introduction into carboxylic acids, their structure, the bonding, some of their physical properties, some of the derivatives such as esters, amides, acid halides, and acid anhydrides, and some features of their acid-base chemistry, such as the fact that they're weak acids with pKs around 4 or so, but that pK can be shifted to lower numbers to make stronger acids when you put electron-withdrawing groups onto the carboxylic acid structure. Okay, thanks for watching.